Dr. Emmanuel Dufourq. He is a lecturer in data science at Stellenbosch University, South Africa, and is with the Department of Industrial Engineering and the School for Data Science and Computational Thinking. So we're kind of going well outside the box here. He is the AIMS Canada Junior Research Chair in Data Science for Climate Resilience. His research interest is now primarily on machine learning for conservation ecology, and his title is The World's Rarest Primate, a Machine Learning Journey. So I'll hand you over to Emmanuel.
Bioacoustics is home to the world's rarest primate, the Hainan gibbon, a species which has experienced a decline in population size due to various factors. Researchers are exploring several conservation efforts to monitor the species, one of which is through the use of passive acoustic monitoring and machine learning, more specifically deep learning by creating convolutional neural network classifier models. My name is Emmanuel Dufourq. I'm a lecturer in data science at Stellenbosch University. I'm affiliated with the Department of Industrial Engineering and the School for Data Science and Computational Thinking, and I'm also a junior research chair in data science for climate resilience at the African Institute for Mathematical Sciences, which are both based in and around Cape Town, South Africa. I'm part of a cross-continental team of researchers working on deep learning algorithms for passive acoustic monitoring of the Hainan gibbon. We published our findings and the approach in a research article in early 2021 as a means of sharing our findings, but also as a means of sharing our code so that other researchers can adapt it to other species. This talk presents the main steps along our journey on using deep learning to create an audio classification model to automatically detect Hainan gibbon vocalization events within large audio files, which were up to 8 hours long. This approach significantly reduces the amount of human expert effort required to analyze vast amount of audio data.
I'm Sam Turvey. I'm a researcher at the Institute of Zoology, which is part of the Zoological Society of London, and I've been involved for about a decade on a long-term conservation programme for the Hainan gibbon. The Hainan gibbon is one of the world's rarest mammals, and it's the world's rarest ape. It was originally found across pretty much all of Hainan Island, which is China's southernmost province. Up to the 1950s or so, there were still several thousand gibbons found across the island, which was then well forested. But the species experienced a precipitous decline in the second half of the 20th century due to a combination of deforestation and hunting for food and traditional medicine. And by the end of the 20th century, there was only a single gibbon population left within a single protected area, Bioacoustics National Nature Reserve in Western Hainan. So it's really important, given the perilous conservation state of this species, to have really effective monitoring in order to understand the status of the population, if that population experiences any changes or declines or any unexpected dynamics, so we know that if any changes in conservation management are required. Traditionally, the way that the Hainan gibbon and other gibbon species have been monitored is by using acoustic monitoring, whereby teams of people in the forest will listen out for gibbons singing and then will locate the gibbons based on their song in the early mornings, which is it's effective, but it's very labour intensive. It's been recognised as a conservation priority to see if there's any other ways that can be used to monitor gibbons using different novel technologies, in particular using passive acoustic recording. So by placing acoustic recording devices within the forests of Hainan to see whether you can detect gibbon calls. So gibbons call pretty much every day if they're in a social group, and it's partly to strengthen the pair bonds and the social bonds within the group, but also to display to other gibbon groups in the landscape that they're there and it's their patch. There's only a few groups of gibbons left within Bawangling, but they still call regularly. In 2016, we trialled a pilot study. I say pilot study, it's for 6 months, so it's quite a long pilot, between March and August of that year, in which we had 8 song meters placed within and around the geographic ranges of the 4 social groups of gibbons that were then present within the reserve.
Hi everyone, I'm Heidi. I am the project coordinator for the Hainan Gibbon project at the Zoological Society of London. And most of my job involves coordinating research, which includes collecting data for projects like this, and also working with local governments, local researchers, and other NGOs, both in China and internationally. So how we collected the data for this project is, first of all, we got a grant from Wildlife Acoustics, and we obtained 8 song meters, which are acoustic recorders, passive acoustic recorders that we then took to China. But first of all, we had to set the program in the machines for them to record the gibbon calls when they call, which is very early in the morning. Another additional challenge was that the manuals from the song meters and the programs, the devices themselves, are only in English, so we had to translate the manual and our specific recording program into Chinese for the rangers in Bawangling Reserve to be able to use. In total, we deployed 8 machines. 4 were placed in the home ranges of 4 of the gibbon groups that were known at the time, and 4 other machines were placed in between groups to try to capture between these groups. Another very important aspect of our work is to improve local conservation capacity. In this case, it meant trialing different technologies and different methods that were totally new to the rangers in Bawangling. And it was both challenging but also very rewarding to work together with them to make it as easy and as smoothly as possible for their data collection, but also to help us understand better the needs and the requirements for to collecting this kind of data.
I'm Jessica Bryant, and I'm now based at Roehampton University, but I did my PhD and a further 3 years of postdoctoral research on the Hainan gibbon during my time at ZSL. And during my time, during my postdoctoral work, I thought, well, we're using gibbon songs to locate and track and understand population size for the Hainan gibbon. Is there a way that we can do this in a more automated fashion to help reduce the number of hours and the physical field effort that the field team of Bawangling National Nature Reserve have to use to try and monitor the Hainan gibbon? So it was my job, or my role within the project, to design and implement the field strategy, so the data collection strategy, and I also led the field team in the deployment of the song meters out in Bawangling.
I'm Christina Stender, and I work at ZSL London Zoo, and I have been for nearly 8 years now. I volunteered my time at the Institute at ZSL, which is where I got introduced to the project of automated detection of Hainan gibbon calls as well. My role basically was to detect any gibbon calls that were collected from the data. I used the Audacity software program, which is where not only could I hear them calling, but I could also see it. So the line here is an actual gibbon call. Once I had located the call itself, I would then type it into a spreadsheet where I would label the file. I would label the start time of the call and what time it finished, and within that period how many calls I would hear, and also if there's any other sounds besides gibbons, like birds or insects or heavy rain for instance, I would also put that in there.
My name is Amanda Hoopner, and I'm from the University of Utah. The main issue still persists though. Now that we have these thousands and tens of thousand hours of recordings, how do we find these instances that we are actually curious in, these vocal events?
The resulting audio data from the acoustic survey is unannotated. What this means is that if we want to train a machine learning classifier to automatically find gibbon vocalization events, then we need to create a dataset by manually going through some of the audio files and annotating part of the files which contain gibbon vocalizations. In our more recent work, we now use Sonic Visualizer to annotate vocalization events, as we can easily write computer code to read the annotations. This allows us to create a dataset which has two main categories: segments of audio which contain gibbon presence and segments of audio which have no gibbon vocalization presence. In other words, we can now create a binary classification model. Instead of building a classification model on the raw audio amplitude data, we can convert the audio segments into spectrograms which resemble images with time on the x-axis and frequency on the y-axis. The reason for doing this is that this enables us to use convolutional neural networks, also known as CNNs, which are the current state-of-the-art approach to create audio classification models. This approach is frequently used in more recent studies, and machine learning researchers are continuously making great improvements in theoretical ideas which can then be applied in areas such as passive acoustic monitoring.
Hi, I'm Ian Durbach. I'm an ecological statistician based between the University of St Andrews and the University of Cape Town. We use two kinds of neural network architectures, a 1D CNN and a 2D CNN. The input for the 1D CNN is a time series of amplitudes for a 10-second segment of audio, so it's a vector of numbers. For the 2D CNN, the input is a spectrogram constructed from the same 10-second segment, so it's an image. Although the inputs differ, both models have the same kind of output. It's a predicted probability that the input segment, either the vector of numbers or the image, contains at least one complete gibbon phrase. Because we had relatively little training data by deep learning standards, we used simple network architectures that need relatively few parameters to be estimated. We experimented with between 1 and 3 convolutional layers and kept max pooling layers between the convolutional layers to reduce the number of parameters. We found that the best architecture was a 2D CNN with 2 convolutional layers. We trained each model for 50 epochs and evaluated models based on their test set accuracy, their sensitivity, and their specificity. We set optimal thresholds for converting predicted probabilities into binary classifications of gibbon or no gibbon, based on minimizing the ratio of sensitivity and false discovery rates in validation datasets.
We ended up processing roughly 1.5 terabytes of data, and further details of our approach can be found in our research article. Additional new data can be processed, and thus speeding up the time to find vocalization events in any new audio survey. We are, however, not limited to only the Hainan gibbons. I'm collaborating with various researchers around the world in countries such as Rwanda, Botswana, Malawi, and the US and Portugal. I'm collaborating with Carly, a PhD student at the City University of New York Graduate Center and Hunter College. Together, we are creating classifier models to process hundreds of hours of acoustic data from Madagascar to find vocalization events of the critically endangered black and white ruffed lemur. A similar approach is being used whereby a convolutional neural network was trained. Around 70 audio files were manually annotated and used to train the model, which took about 2 to 3 days to process a large amount of audio data. Carly is currently in Madagascar collecting additional audio data, which we will then process. At Stellenbosch University, we are launching a new research group called Data Science for Ecosystems, where the vision is to become a leading collaborative group in the field of passive acoustic monitoring and machine learning. The rationale for launching the group was to encourage ecologists and machine learning specialists to work together more closely and to bridge the gap between the two fields as a means of addressing conservation priority tasks. The field of machine learning is evolving at a very rapid pace, and thus by continuously reading the latest advancements in academic literature, we are trying to adapt and apply them to conservation ecology. While it is true that machine learning can drastically reduce the amount of human effort required in passive acoustic surveys, the algorithms are not perfect, and their performance will drastically be impacted by the data used in the training process. Our current focus is on algorithms that can perform well with very little data, and thus rendering them useful for species for which very little acoustic recordings exist. Most of my time recently involves writing computer code, surveying academic literature, and engaging with ecologists and specialists to provide more useful and sophisticated tools.
Now that automated recording units are more readily available, it really enables just about anyone to use them. This is excellent, from researchers who may be able to use them now to study more rare or elusive organisms to be able to detect them and through their vocal behavior, to other conservation groups who can use these units for anti-poaching measures of instances of gunshots that has been used in the past. With these machine learning techniques that we've used with these gibbons, it really opens up unlimited possibilities. Now that we can reduce the amount of man hours it takes to actually find the real data, these vocal events that we're interested in, it really enables us to ask a lot more questions. So now if we're interested in one population, we could actually broaden that and look at multiple species and populations of primates in that area to see how they actually relate and how their vocal behaviors overlap or not. Further, if we can more easily find these vocal behaviors that we're interested in these automated recording units, then we can more closely monitor these populations of interest, especially ones as critical as the gibbons when we have so few individuals left. This will really allow more real-time monitoring and for conservation managers to detect disturbances or any massive changes and respond accordingly.
Advancements in machine learning provides a lot of hope to enable us to process vast amounts of data at a rapid pace and thus enabling more immediate conservation response. My personal view on the topic is that it is imperative for ecologists and machine learning experts to combine their efforts and not to work in isolation. I would also recommend that academic work does not simply end at a research article and that action is taken to engage with policymakers to have a larger impact and to create tools which are easy to use. Finally, I believe that everyone, experts and non-experts, can play an important role in the area of passive acoustic monitoring and machine learning. Specifically, everyone can help by providing more open access, high-quality recordings of various species on websites such as Zenocanto. For example, here in Cape Town, South Africa, I was the first person to upload a recording of the grey heron, a common bird species in my neighborhood. But by uploading a recording, this allows other researchers to gain access and to train machine learning models, an effect which will scale significantly with more human effort and audio uploads. I hope that this talk has been informative and that I have provided some insights into what went on in our journey of applying machine learning to create an acoustic classifier for the Hainan gibbon. Feel free to reach out via email if you have any additional questions, and also feel free to reach out if you would like to collaborate.
Wow, thank you, Emmanuel. That was wonderful. Once again, I said this right at the beginning, it was more like a documentary. It was brilliant. I mean, it shows that you've got a really good team together, people collaborating from all over the world, which I find a wonderful, wonderful thing to be doing. And I loved your plug of Zenocanto. At the end, I really got into Zenocanto. So if anyone's into birds, upload your recordings onto Zenocanto, or if you want to find recordings of a particular bird, have a look on there. It's a really wonderful resource. We need one for all mammals now. That's what we need. So we have questions coming in thick and fast. The first one is kind of quite a simple question, but I think it's probably all on our tip of all of our tongue. So what do you think the future holds for the conservation of the Hainan gibbon?
So the team on Hainan Island are currently recording more data right now, and we are developing more easy interfaces, graphical interfaces, so that students can use these complex models easily. In the current form, they are a little bit more challenging to use if you're not used to computer programming. So we are basically developing nice graphical interfaces and constantly improving the models, improving the accuracy, which is part of actually the latest research that we are going to publish recently. So at least from a passive acoustic perspective, the work is very much ongoing. Yeah, I can comment on that. As to the actual efforts, I don't have enough information to confirm anything about that.
Somebody's asked, so this is now like way above my head, but wouldn't time-focusing architectures like RRN or some combination also be beneficial when classifying animal language?
Right. So RNN refers to recurrent neural networks, and it's just a very fancy neural network that takes the temporal data into consideration as well. So to answer the question specifically, absolutely. The gibbon work was when I started my postdoctoral fellowship, and I have a computer science background, so I don't have an ecology background. And after my postdoc, I fell in love with passive acoustic monitoring. So now it's basically full steam ahead. We have multiple students tackling very complex methodologies to severely advance machine learning for conservation ecology. So recurrent neural networks, RNNs, is basically some of the things that we are exploring. And we are actually developing an AI for AI. In other words, we build artificial intelligence algorithms to find the best artificial intelligence algorithm to do passive acoustic monitoring. So it's a very active area of research, and we're very excited by what we're doing in our group. Yeah.
Wow. Will it have a third stage? AI?
No.
Regarding recording of the Hainan gibbons, is it possible to identify individual gibbons or sex or maturity of the gibbons and particular interactions between individuals from your acoustic recordings?
Yeah, so that's a great question. So one of our students at the University of Cape Town, Noni, she's exploring whether we can use machine learning to differentiate between the different groups, because there are different groups, and we want to know, can we actually differentiate between them? So I won't give any spoilers just yet. We'll just have to wait for her to submit her thesis. But we are trying to work on group identification, and with collaborators at Stellenbosch, we are trying to investigate individual ID for amphibians. But it is very challenging, so there's a long road ahead.
Yeah, yeah. Do you plan on distributing this or other data sets? Do you plan on distributing this data set using something like DAT, which being peer-to-peer requires significantly less infrastructure?
Absolutely. So not all the data. So we had 1.5 terabytes of data. We were only able to upload, I think it was 150 gigabytes to Zenodo. So all the data that we used for the machine learning classifier, and a lot more data was made publicly available, and all the software code was made publicly available as well. So our philosophy is to make everything available, to share it with everyone so that they can work on it for their respective species as well.
I'm really impressed with these questions, because we like the first two speakers were obviously very, very hands-on with the primates. You're taking a step back and doing everything from where you are now, and the questions are coming out exactly like this. So what programming language did you use to develop your AI algorithms, and why? And how large were your data sets?
Okay, great question. Okay, so so for the gibbons, it was 1.5 terabytes. For the lemurs, it's a couple of terabytes. And of course, we have other data sets, because now I just love this. So I have a bunch of recorders myself, and I have terabytes of data. I actually had to buy 3 new hard drives recently. I just can't keep all this data. So basically insane amounts of data, right? And we processed the final data on AWS server. It took 2 days and cost about $80 to do so. That was then. Our current research is finding that we can do this a lot more efficiently for a lot less cheaper, not requiring specialized hardware. But that paper will hopefully be released in a few months. So that was a question about the data sets. In terms of the programming languages, all general audio processing was done using Python, which is open source, so that's the why. And the development of the neural networks were done in TensorFlow, primarily because there is a large community support for TensorFlow. So if you're stuck in your development of the code, you can just Google something and you'll get an answer. So there's a lot of support. So that's why we chose those ones, and I teach those ones. So it's the easiest one for me to use.
It's popping up in the chat. I think people have got thumbs up and high
yeah,
five.
Python.
Thanks for your talk. Have you looked at identifying individual gibbons through their unique long calls to help monitor specific groups spatially and temporally?
Not yet. So we're tackling the group identification first, and then based on the results, we will either attempt or not attempt based on the findings. But these are things to investigate. We don't have the answers right now.
And this is how long's a piece of string here, but it's a very good question. How should one approach learning more about CNN stroke deep learning systems and then applying it to bioacoustic research? I find many data science traineeships, but don't see the connection between ecology and data science.
Okay, so actually next month, I am hosting a workshop on teaching people an introduction to deep learning and bioacoustics. But I have recognized that there is a lack of courses and tutorials on applications of deep learning to bioacoustics. So this is something that we are in the process of developing via courses and tutorials. So you can expect more from me on that soon. In terms of just learning about general deep learning, there are wonderful courses on Coursera. That's usually what I recommend to people. The deep learning courses on Coursera are taught by leading experts. So I would start there. And then hopefully by the time you finish that course, our new material on deep learning for bioacoustics will be out so that you could learn more about that.
I mean, I think it might be worth putting something in the chat, because there's people in the chat that say, "Oh, please tell us more. Where can we find these courses, etc." So there might be, we might need to sort of give you all a mail out or something like that, just to keep you informed of where they all are. What are the advantages of using deep learning in comparison to cross-spectrum correlation? Also, as most applications of audio in deep learning use recurrent neural networks, was there a reason why this architecture was not suitable? Also, how much larger do you think the training set would need to be to create an algorithm that could classify individuals as well as detect species presence? Whew.
Okay, so we did explore recurrent neural networks, the RNNs, and we found that they weren't suitable for our data sets. So we did try multiple different architectures. But when we develop the so-called AI for AI, this will enable us to explore every possibility that exists in terms of architectures. So this is a sophisticated methodology that we developed in my PhD. It's called Eden, but we're hoping to develop a new one for ecology. And that will explore the RNNs, but we did explore them. And how much larger the data set would have to be to do individual ID, I don't know. I suppose the real question is, to what extent is it even possible to do that? I think it would be based on the methodology. My gut feeling suggests Siamese neural network. And one of my master's students is exploring that topic to see if we can explore some of that. I can't remember the first part of that question.
What's the advantage of using deep learning in
right.
spectrum correlation?
So I don't know about the latter method, but I can comment on the rationale for using deep learning. And the rationale for that is basically that if we turn to the academic literature on speech recognition, we see that deep learning produces state-of-the-art on practically any audio and speech recognition classification problem. And we also see great trends in academic literature and ecology, suggesting that deep learning also is state of the art. So I don't know about the latter technique that was suggested, but all academic literature points to focusing on enhancing and advancing deep learning for passive acoustic monitoring.
And these questions are still sort of flying in, but I am aware of time, but we'll try and get a couple more done. We are currently working on integrating AI software into our lab, but we're in the cleanup stage to improve accuracy and prevent error. About how long did it take your project team to work out the kinks when using machine learning? Or are you still working out the kinks? Is that
no, so okay. So basically, that part of the research was part of my postdoc. So it was something I was doing very actively, exploring different architectures and exploring a whole bunch of different hyperparameters associated with the deep learning architectures. So, I mean, it was a bulk of the time. But as I said, more modern techniques can allow us to optimize these networks, which reduces the programmer's effort, so to speak. So I highly suspect that the future of this will be even less time consuming for the developers, basically, as the techniques improve. Yeah.
And we've probably got enough time to squeeze two more quick questions in. Will your algorithms be made available to any researcher? And if so, where can we stay up to date on the progress and release of these? And thank you for your amazing presentation.
So absolutely. So everything is and will always be open source. So that is something that I strive to do as part of the contribution for ecology. So staying on top of our latest developments, one way to do that is just follow me on Twitter. And basically we'll just share as things become more available. And I'm hoping that this year we will have a lot of contributions because I have a lot of students working with me, and we're hoping to get some new postdocs, and that will drastically increase our output. So if you just chat with me on Twitter, and basically I'll keep you up to date on anything new, and everything will always be open source.
Your cat is basically stealing the show right now.
Yeah, I think she wants supper.
She looks like she's perched on your shoulders. One last question, really, just to finish off. But given the rarity of the Hainan gibbon, was it difficult to obtain enough data to train the CNN? If so, how did you overcome this? And related to this, another question: how many samples do you recommend to use as training data for machine learning? Is there a minimum number?
Okay. So let me take the last question first, because it's something I'm very passionate about. So my current area of research is how can we build the most reliable classifier with the least possible data? And the paper that we're hoping to publish quite soon shows that we can create fairly robust models with as few as 25 verified annotations. This is on the lemurs, gibbons, and the Theoloalethi from Malawi, and 2 bird species in Cape Town. So with as few as 25, we can get pretty good models, but more details will become available in our new paper. For the gibbons, I actually manually annotated 150 hours. But that's not something we have to do anymore, because the advancements in deep learning and machine learning suggest that we don't actually need to do that anymore. So things actually have moved really quickly between the last publication. So for the gibbons, we had about 1,000 or so verified annotations, but it's highly problem dependent, so you can't give a single number. But once our latest research is out, please have a look and see if you can actually build classifiers with as few as 25 or 50 cores, which is super imperative for species where we have very little verified data, such as the Hainan pheasant peacock, where we only have 3 verified cores.
Wow.
So that's an interesting challenge to see if we can crack that.
Yeah, I met with a student in India that was looking, I can't remember what bird species it was, but they had one recording from 1974 or something like that. And it was, can we create a classifier with this one recording? Like, what? No, who knows? So that's what they're trying right now. One quick thing that's just appeared in the chat, we're trying to keep an eye on it, is can you tell us what your Twitter profile is? We'll tweet it as well, but
it's basically just my full name and full surname. Okay. So it's at Emmanuel Dufourq.
There you go. So you heard it here first. So please go and follow. Thank you so much, Emmanuel. That was so good, and thank your cat as well for appearance. It was a really wonderful talk. And I say there's still one or two questions. If you're still happy to type away in the chat, then please do. So thank you again. Big round of applause from the world once again.
Thanks, Paul, and thanks, Wildlife Acoustics.